Hello, my name is Scott Miller, and I'm the instructor for this course. The purpose of this video is to go over proper graphing techniques. My experience with this course is that students either don't know how to create a graph properly or choose not to. Either way, it negatively affects the grades on their lab reports, the sole item for determining a grade in this course. Now, I can't help those who are choosing not to do a graph or graphs correctly on a lab report, but I hope to offer some help to those that want to do them correctly so that it will positively affect their overall grade in this course. To begin, we need some data. We are going to do these graphs by hand. In a later video, we will do the same using Excel. Once we have the data, we want to prepare a piece of graph paper so that the data spans most of the paper. Some graph paper has a grid that spans the entire piece of paper. Some has a border. For these labs, either works depending on what you can find or have available. In this exercise, I'm using one that has its grid span the paper. I like to move up from the lower left corner of the page 3 or 4 blocks for both the vertical and horizontal directions. This will leave room for axis labels. Graphs must communicate what you have found from the data, so the more information you provide on your graph, the better for anyone looking at it. The dot here will be my origin. I have already counted the number of blocks in both the horizontal and vertical direction. I don't normally write these on the graph, but in this case use it for simple illustration. If you use the same type of graph paper for the lab reports in this course, you will know this count and can use it each time. Since I have already determined where I want to place my origin, I can now draw in the axis lines in both the vertical and horizontal directions. My intent is to span this paper with the data, so I take each line to the edge of the graph paper in both directions. Here is the data from the robot. To properly span the graph paper, we are interested in the maximum values of each data column. In this case, the maximum number in the time column is 25 seconds, and the maximum value in the distance column is 5.97 meters. A look at my horizontal axis shows a total of 35 blocks. I could use this information for creating the time axis, but that last block has its line on the edge of the paper and cannot be seen. So another number may be better. In this case, I will let 30 blocks represent my 25 seconds. I can then set up a ratio to determine what number of blocks represents what number of seconds, choosing to represent 5-second intervals, and this would be completely your choice. If you want 1-second tick marks, that's fine, though it will be a little busy if you do it. My ratio says that every 6 blocks will be 5 seconds. On my graph paper, on the axis that will represent time, I count off 6 blocks, and each 6 blocks make a tick mark. I can then label the tick marks and write the axis label for the horizontal line, including the unit. I do the same thing for the vertical axis. The number just bigger than 5.97 meters is the distance column would be 6. Sometimes a whole number will be useful. Sometimes you might have to have a number with a decimal value. The choice will be what works best with the numbers of blocks you want to use to span the data along that axis. So trial and error may be your recourse. But if I choose to make 48 blocks represent 6 meters, I will be spanning the graph paper in that direction as well, with every 8 blocks representing 1 meter. Notice that I don't have to use the same scale on both axes. I treat them independently and choose that scale which works best with that data set. Applying this scale to the vertical axis, I apply tick marks, label each of those tick marks, and label the axis, including its unit. Once the axes are complete, it's time to plot the data. As care has been taken to identify the scale on each axis, there is knowledge about how much each block is worth in both directions. This will allow the placement of dots on the graph paper pretty close to where they should be. If we had made a small graph, this set of data would look almost linear, but making it large, spanning the full piece of graph paper, one can notice there is a curve here. If we consult our physics textbook, we find that a graph of distance versus time has a parabolic shape if the object in question is accelerating at a constant rate. So apparently the robot was doing this. Notice in the textbook that a continuous curved line is used to represent the complete data set. We do not see a connected dots graph in our text, so we should not produce one here either. Instead, we can freehand sketch a smooth curve through the data. And as a last step, once the data is represented by the curve, we can add an overall label for this graph to indicate what is being plotted against what. Although this is a good representation of the data set, it would be useful if we could do a graph that allows us to come up with some sort of equation representing this kind of movement, just like we find it in the text. Calculus could be applied to this curve to do such a thing, but it is possible for us to do so using algebra, assuming we can convert this graph into a straight line graph. For a linear graph, we can use the equation for a straight line to fit the data. In the case of a physics experiment, y would be whatever variable is on the vertical axis, x would be whatever variable is on the horizontal axis, b would be the value where the graph passes through the y-axis, which is why it's called the y-intercept, and the slope of a straight line can be pulled from the graph once it's drawn using points that fall on the line that are generally not the data points that we ourselves have measured. Now the reason one does not use data values is that the line one draws through the data is a trend line. Generally, one lays down a ruler or other straight edge and draws a line through the data that best averages the data set. Some data pairs may end up above this line, some below, and some will fall on the line. But this is your best guess as to what the average line should look like, so you want the slope of this line, not a slope based on the values that may or may not have errors associated with them. So the data pairs x1, y1, and x2, y2 need to come from the line once it is drawn, and it is the slope of this line that is to be determined. In this case, our textbook leads us to try something that might cause the graph to become a straight line. That is, one might try squaring the time values and plotting those squared time values against the same distance values. Squaring 25 gives 625. Since the goal is to span the graph paper with this new graph, 646 turns out to fit the bill. Setting up ratios again, every 5 blocks represent 95 seconds squared. Tick marks can be placed and numbered, and a new label is now used because we're now plotting squared time. Since the distance was not changed, we can use the same scale factor we used in the previous graph. Now that all that is needed is to plot the new data pairs, lay down a straight edge, and draw the best line representing the trend in the data that can be done. Notice not all the data points fall on this line, and we did not play connected dots here either. We can now pick 2 points based on the grids that fall on the line we drew by finding points along the line that pass through grid intersection points. Since we chose the scale for creating this graph, we should be able to identify each intersection point both from the horizontal and vertical axes. We mark them in a different way on the graph to distinguish them from the data points. It can also be helpful to put down the pair of numbers represented by those points. This makes calculating the slope easier in case we make a number crunching error, as we can always look back and make sure we chose our x and y values in the slope calculation correctly. This brings us to a second item that should be put in the lab reports, a calculation page. In the lab reports there are to be done for this course. There will be calculations to complete. Some may be a slope calculation. Some may be the result of putting data into some equation and coming up with some answer. All such calculations should be demonstrated on a calculations page and submitted in the lab report. It is not necessary to repeat the same calculation over and over with new data values, but it is necessary to put one set of data through the equations of interest to demonstrate that you know what is to go where in that equation. If you do the rest of your on your calculator and list the results in a table, either provided in the lab report write-up or one you create yourself on the calculations page, that is fine. But one example should appear explicitly stepped through from the equation with variables, the equation with the data inserted, calculation steps as necessary, and the final answer. In this example, we are demonstrating the placement of values from our line graph into the slope equation. Notice that units accompany the numbers in the equation and that there are units on the final result that come out of that calculation. The same will be true for most calculations you do in these lab reports. So in conclusion, we have seen how a graph can be used to show how two variables are related to each other. But to clearly see the relationships, the graphs must be done properly. We will be using graphs in many of our lab reports to verify some of the relationships that are covered in the corresponding physics course related to this lab course. Feel free to refer to our textbook to see how those relationships and the results of our lab graphs match up.